Okay, so today we're talking about modeling. That's a very general topic. Um, does that say model? Looks like it says molding. Okay, modeling. Okay, so there's a couple of general statements I wanted to make about this because it is a very general topic. Um, First of all, um, when we talk about one thing being proportional to the other, if A is proportional to B, we're going to translate that mathematically, right, to say that A is equal to K times B, where K is going to be the constant of proportionality. Okay, and similarly, if A is inversely proportional to B, that means that you can write that as A equals K divided by B. Okay, the last thing before we get started on our looking at some of the models we've had before is just kind of a philosophy, right? What we're doing is we're modeling the rate of change of a thing, rate of change, and not the quantity itself, not the thing itself. And what do I mean by that? Do you remember our discussion about the population models? We said if I have a population over time, yeah, I can probably get some data, right? Oh, it's probably not going to look that nice. Okay, here's some data. Okay, and so one way I could model this population is I could try to find some curve that somehow best fits the data. Defining that more in depth would take us too far afield, but somehow it is possible mathematically to define and find a best fitting curve through that data. Okay, the problem is once you have that, what does it tell you? Well, not much. It tells you what the function is, and you might be able to do some prediction outside the time interval, but those predictions become very untrustworthy, and so we don't want to try to we don't want to do this unless we have to. Is the idea. You don't want to model the exact data unless you absolutely have to. So instead, what we do is for a population model, for example, we said P prime is equal to KP. Now, why is this a better model than that? It's because this, for one thing, it tells you exactly what the assumption is on the model. This is telling us that the rate of change of the population is proportional to the population. Done. That's the only thing we're modeling in this model of population. And so from this, you can also get, right, the P of T is an exponential model. But of course, this tells you a lot of information about your underlying assumptions. Okay, so this is kind of the gold standard. A differential equation is going to be a gold standard for being able to write a model for a mathematical object. Okay. Now, having said that, let's take a look at a few of our models. Speaking of population, so our population model, something of the form, say P prime equals R times P minus K. What would that be? Well, we've already said that this is a population, or this is an exponential growth. So what does subtracting a constant mean to your population growth? Well, this is, how do I want to say this? Culling the population at k units per unit time. Okay, so we'd have to be sure that our R and our K are using the correct units. But this is saying that we're removing K individuals from the population, however you want to say that, per unit time. So this could be like the population could be running per month or per year, and so we'd have to change our units on our R and our K to match either the per month or per year time frame. Good. So that's our basic population model. Our basic falling body problem is mass times acceleration. Remember, acceleration is the derivative of velocity. And then we have our downward as positive, giving our weight, minus gamma is our constant of proportionality, times v. This is assuming, this is an assumption, I should say. Assumption. Sometimes our textbook uses v squared, sometimes use v squared, but that would have to be told to you. If we're just looking at the basic model, you can assume that the air resistance, that's what that is proportional to, and that's why we have a constant, the velocity. Okay, and so that's the falling body problem. M is mass, right? G is the gravity, so metric, G is about 9.8. Okay, then we have the law of cooling, Newton's law of cooling, right, which says that the rate of change of the population of the body is proportional to the difference in temperature between the temperature of the body and the temperature of the environment. Why do I put a minus there? It's because, for example, if I have hot coffee in a cold room, right, I'd want my derivative to be negative, and so usually if we put in an arbitrary constant, we think of that arbitrary constant as being positive. Okay, and so this would give us our model. Good, so these are just three models that we've already discussed. I should also say that we know how to solve y prime equals ay plus b. Do you remember how to solve that directly without having to do anything? Because this is really, it's nice to just be able to write down the solution. Y of t is going to be equal to ce to the at minus b over a. Okay. I say that it's nice because now you can solve all these other differential equations directly, right? What's our population model solution? Well, it's ce to the rt minus the b is the k, minus minus k, there we go, minus k over r. So that's going to be ce to the rt plus k over r. Okay, good. How about the falling body problem? Well, you have to do a quick rewrite to get the constant right. Right, but once you have this, now you can go ahead and write the solution. It's going to be ce to the minus gamma over mt, and then minus g over minus gamma over m. Okay, so you could rewrite that. mg over gamma. Very good. All right, that's our falling body problem. Now, how about Newton's law of cooling? Newton cooling, I'll just say. Can I just write down the solution from that? Oh, you betcha. U is equal to ce to the minus kt plus t. There you go. See? These are easy. So again, I'm only saying this not to impress you, but just to say, if we know the solution to this directly, then these models are just really easy to solve then, right? You can just write down the solution without having to think about it too much. Okay, very good. All right, so now let's see, it's about 10 minutes in, so I'm going to pause here, and in the next video we're going to start our first model. And just in general, we're going to remember that the rate of change of something is equal to the rate in minus the rate out. And a key part of doing the modeling is going to be keep track of the units. If you've had physics, you know that units plays a key role in keeping track of everything, keeping everything straight. Okay, so we'll be back in just a moment.